So our presenter is Nicole Bola. She's a professional engineer in Minnesota. She has a degree in chemical engineering and a minor in environmental engineering from the University of Minnesota Duluth. Her background previously was focused on nutrient removal with biological processes and has recently moved to the lead sales of a new innovative advanced electro-oxidation technology. Nicole is excited to use both her chemical and environmental background to better understand this technology and help bring it to market. I'm very pleased to hand this over now to Nicole for the presentation. Thank you.
I appreciate you tuning into my presentation. I know this is all a little bit new, and I appreciate the group too for setting this all up. It's been really great, all things considered. I know it's difficult to do things virtually with everyone remote so quickly, so thank you so much for that. And thank you, since I still, so I live in Minnesota, so I still got to participate, and so I really, really do appreciate that. Anyway, we'll get into it. So basically today we're going to be talking about advanced electro-oxidation, which is our kind of special patented technology, and we're going to really focus in on its use for wastewater. So we'll go over a little bit about what it is, how it works. For any of the chemistry nerds out there, we'll get into a little bit the chemistry behind it too. It helps, at least for me, kind of put it into context compared to other types of technology. We'll also go over, what it can do. So what the technology, at least our testing has shown that it can do. And then also how the system and how, that would look in a real life setting and how it operates. We'll also go through some data and some different curves and graphs and pictures, hopefully, so this isn't as super dry and boring for y'all. And then if we have time, we'll go through a little bit of bonus in-field data too. So what is advanced electro-oxidation? Basically, it's similar to like an AOP process. So you are creating all of these oxidative species and utilizing those to destroy different types of contaminants that are actually in the wastewater. So the way we do this is by running DC across our array of electrodes, so cathodes and anodes. And by doing this, we're taking both the water and then chlorides that are already present in the wastewater and creating oxidative species from there. And so your big inputs, other than the actual wastewater flowing through the system, are electricity, so DC, and then also if there isn't enough conductivity existing in the waste, or we may supplement that. But for the most part, this process doesn't require a large chemical addition as well too. And so that's what makes it a little bit different than maybe other AOP, advanced oxidative processes that you might be more used to. And so the outputs that we're getting from this is ozone, chloride ions, hydroxyl radicals, hydrogen peroxide, in varying levels, and that's what's doing kind of the actual hard work for you. So this is kind of a nice visual to go over what's happening too. So the wastewater is flowing up through the system. You're creating these oxidative species. They're destroying the contaminants. And then your waste stream, if you will, is going to be the electro-decomposition gases. And so that's what you'll mix with ambient air so that's safe to emit. It's typically not a large enough amount of hydrogen to capture and use for fuel, but it might be an option. Say you already have a cogen system, you're already utilizing methane or something that you're creating on site to burn, you would potentially be able to add this to that system to increase the BTUs of that existing system. But typically what we're seeing, even with a little bit higher flows, it's a small amount of hydrogen that you're creating. And so the other thing too that's kind of unique and different is we're not running that current constantly at a certain rate across the electrodes. We've kind of optimized that where it's being pulsated both to save energy. And then what we've seen is actually it helps with the reactor kinetics of the system too. So it runs more efficiently. And then we're also alternatively, we get to save energy that way too. And we'll get into it a little bit later, but you can also turn the electrodes down or even off depending on, if you're at a municipal wastewater plant and you're dealing with diurnal flow patterns, right? So when there's a higher concentration, you may run more electrodes than if there's a lower concentration. So the other thing too, I guess worth mentioning, the electrodes themselves are patented, and that the material of the electrodes is dimensionally stable, which means that the electrodes are not sacrificial. So they're not giving up some of their material to be able to create these oxidative species. And it matters in the sense of longevity, because if you have a sacrificial electrode, you're looking at weeks to maybe months where you can operate, but eventually you'll run out of material. And because they're dimensionally, and then you'd have to keep going in, every 2 to 3 months and swap those out and put new ones in. These electrodes, though, they're a little bit, have a little bit fancier material and different coatings on them. Because they're dimensionally stable, they're good for the, 10 to 20 years, depending on the particular application that you're looking at. All right, so kind of the background here. Basically, you have two major things that are happening at the same time. You have what is called direct oxidation. So that's where we're getting a lot of the organics destruction, if you will. And it's happening kind of at the surface of the electrode. And then you also have indirect oxidation or mediated oxidation. And basically that's what's happening in the kind of bulk fluid around the system. And that's where you're getting a lot of those chloride ions are destroying ammonia. So it's very similar to it's easiest for me to understand is it's like a breakpoint chlorination where you add chlorine to destroy ammonia. It's similar in that sense in terms of an actual chemical equation. The big difference is we're not seeing a strict dependency upon pH. So we'll get really good destruction rapidly, regardless of the pH of the system. The other thing that's cool too that we just recently tested is even at an elevated level of solids. So say you have a supernatant stream where you're treating perhaps like or maybe a side stream ammonia treatment for a number of reasons that may have solids in it, that doesn't seem to interact or significantly affect the process, even at pretty high concentrations. So that's cool. The other thing to note too, it's kind of obvious, but basically because you're not creating nitrifiers, the biology that breaks down ammonia to nitrates, we're not creating these nitrates and nitrites. So we can also hit a very low total nitrogen out of the system. You're getting both, if you will, nitrification, denitrification, right? You're destroying that ammonia directly to nitrogen gas. So there isn't that intermediate kind of stage that you may have to deal with depending on your. And then I kind of mentioned it before, those electrodecomposition gases. So, one big benefit potentially of this technology is that you're not creating methane, and you're actually creating quite a bit less CO2 than perhaps our traditional wastewater system would. So these numbers are actually from a study out in Ontario, and just showing like a typical extended aeration, just a standard process with a digester. So that's where you're getting those values from versus, what our system would look like at a similar, flow rate, if you will. And so here's kind of a snapshot of the overall capabilities and most of the contaminants that we've tested for destruction. So what we're seeing is pretty much complete ammonia removal. Often we'll get the ammonia to non-detect levels, and we're seeing anywhere from 2 to 4 typically for a total nitrogen on the municipal wastewater that we're testing. Then you'll also see we've done some sulfide testing and H2S, phenols, polyvinyls. A lot of those are from, and boron too, are all from landfills. So we've done some work treating landfill leachate. And then often what we'll see is we get about a 40 to 60, around a 50% BOD or COD. reduction. So we do not, with this process, get rid of all of the organics. So it's a good complementary process to maybe, like if you have a simpler lagoon, like a flow through system where you're getting good BOD removal, but perhaps you're struggling to nitrify during the winter time. But I won't belabor that too much. We can get into the actual numbers. The other kind of piece of information too that we have is with a lot of the kind of ozone and the hydroxyl radicals that we're creating, we'll get a significant amount of pharmaceutical destruction as well too. And so that's just kind of what this chart outlines. We're doing some work actually with UMass, the group that this data is from, to update everything. They have a really new cool mass spectrometry equipment. So if you have anything weird that you're trying to test at all, we're always game for stuff like that. And so here's kind of what it looks like. The other thing to mention is we'll also utilize instrumentation in the process too. So we'll have often an ammonia as a feed forward. So we'll have that up front in the process to augment both potentially the salt dose and then the actual how often the electrodes are running and the current density that we're running over the electrodes themselves. And so here's kind of an overview of what that would look like basically in the system. You have on the far left, just your standard PLC HMI. So, the brains of what's happening. We also incorporate a clean in place system. So that will be driven there, similar to like an MBR or, maybe an RO system where you have that kind of clean in place automated. Then you'll have the kind of darker gray boxes are the reactors themselves. So that's where the electrodes are. And next to them is their respective power supplies. And it's important to have that power supply really close to the reactor. The farther away those things are, the more losses you have. So everything's packed in really tightly to keep it as efficient as possible. And then, so you see the other tanks will have your tanks for acid backwash, or if you're supplementing any chlorides as well too. So overall, pretty simple. This footprint here, probably anywhere from, I always think of things in gallons, but a small community, small and mid-sized community would be able to treat all of their wastewater through this system. So kind of getting into the actual data that we're going to go through. Well, I've been working in conjunction with University of Massachusetts out in Amherst, Mass. So the other side of the world from you guys, but also near the coast. And so they are a really great group. They're kind of uniquely poised to help different kind of small systems, and they work with this WINS group, which is connected to Carollo and WEF as well too. So really cool consortium of a lot of different new innovative companies. So definitely just a plug to check them out if you're ever curious about new stuff that's happening. Their laboratory's really impressive. I kind of mentioned they have a cool mass spec that we're utilizing for some different, hot topic CEC nasty contaminants that are emerging that we're looking at testing over there. And then, so this is kind of an overview of what the system looks like. They, like I said, are uniquely poised, and that being their university is really close to the city's wastewater plant, which is a pretty standard externalization process where they have actually primary and secondary clarifiers, which is nice. And then they also digest their solids and have a drying facility. So they have all sorts of different streams that you can take from. They even have both surface and aquifer water too to test for drinking water. So it's a really cool site in that sense. And they'll take, and what a lot of our data is predicated upon, is their actual municipal wastewater from the city itself. So they pipe it from lots of different locations, and we in the data here are taking it from their primary influent. So the solids are settled out, but the concentrations are still reasonably high for BOD and ammonia, and that's kind of what we're looking at testing. We're really focused in on that ammonia destruction. Both to be able to kind of size systems preliminarily, if you will, but then also to kind of understand the kinetics of that reaction better too, since it happens really quickly, but it does kind of slow down at the lower concentrations. So just getting a good handle on that process so we can ensure good treatment for people. So here's Chris here, one of the graduate students at the university, and that's the influent tank, actually, I believe. The goal of the system, like I mentioned, is to kind of understand that rate of reaction really well. And what we did is we varied the conductivity, so existing and then also adding salt as well too. And then we also varied the actual current density that was applied to the electrons themselves. And so what we're doing is making sure we're getting ammonia destruction, we're not creating excessive chlorides, and then also figuring out kind of what current levels are optimal for treatment. And so here's kind of the bulk of the work we did and what it looks like. So it's a lot of lines, and I've tried to kind of distinguish them, but basically you're starting at, kind of higher level, a little bit over 50. And if, like often when the university students were in town, of course, their concentrations went down. So sometimes we would supplement that. But 50 to 55 in terms of a milligram per liter ammonia, and then taking it all the way down to basically a non-detectable level. And that this was run through the pilot, and anywhere from 20 to, you can see in this next chart here, a little over 30-40 minutes, you're getting removal, and that's at a batch process, just to be able to watch that curve. But basically, if you're running it as a kind of a flow through system, is actually quite a bit faster than that. So typically what we see when we're piloting is 3 to maybe 10 minutes at the most of retention time. So fairly small footprint, fairly quickly where this happens. If you look, the kind of dashed lines, if you will, are at that higher current density, and the solid lines are at that lower current density. And then we're kind of varying the salt doses. So the more conductivity you have and the more electricity that you're running through the system, the higher level of current, the faster the reaction happens. So nothing groundbreaking there, pretty obvious, but just trying to get a handle on what's optimal. And then, as you can see here too, there's certain levels where the conductivity and the current was so low that we just weren't getting to zero. So important in that sense to understand that interaction. So here's kind of a simpler way to look at it. Basically, as you increase the conductivity, you're increasing the removal rate, but the interesting thing is we kind of saw a steeper increase in the removal rate at that higher amperage, so at that higher current density. So it's not completely straightforward or linear in that sense. And then, so this is based on a removal rate where you're taking milligrams per liter, so, or ppm, so 30 ppm per retention time is how that is rated there. And then the different levels of conductivities on the bottom. The other thing that's interesting, worth noting too, in different communities that, and I know in Minnesota, they actually salt their roads. And then of course, with people and their water softeners are sending chlorides into the system naturally. And this way, since we're measuring those as well too, we'll even get to use some of them up in our process and be able to kind of augment the process that way. So say you have an increase in chlorides coming into your system, you might be able to turn down the current density that you're running the plant at. So again, just kind of another better level of understanding to incorporate process control. And then the other kind of thing that they helped chart here too is basically, as you're removing ammonia faster, it's going to cost more per quote unquote batch, so that they ran through the system basically, which makes sense. And then that's also something that you can play with depending on where you are and how much energy costs versus salt versus capital, right? So if you're running at a lower removal rate, you're going to need more reactors. But then you can maybe potentially save on your O&M down the line for energy consumption. So just another facet to think about when you're planning out for that 20, 30 year, right? And so that's kind of what I hit on there. Basically, a lot of it's to understand the curve, but then also to understand what the O&M kind of looks like too over time. One other thing we tested for was the destruction of E. coli as well too. Since you're creating chlorine, ozone, you're going to get destruction of that as well. And so during this test, we didn't spend a lot of time trying to nail down disinfection, just more of you know, some preliminary understanding that that's happening as well too. So one other thing that's kind of cool about the system, and I apologize that the left beaker is a little bit empty. We used up all the sample treating it. So we actually ran this through the pilot facility. So I believe it was about a 100-gallon jug or so that was sent and then run through the large pilot, because we then in turn, once we had processed it, sent it back to the customer because they were running it through an RO system. So this is kind of a pre-treatment step, if you will, for that. Both to, you know, save on the longevity of the RO, and then also to help with this particular site was struggling to get boron removal, which was something that was a little bit new to me, but the location here needed to meet a groundwater level standard. So instead of discharging into receiving water body, they're actually discharging to the ground. So that's why they need to meet that kind of groundwater level standard, if you will. Hence the boron removal. And that's kind of what we looked at here. So the other nice thing in the picture shows that we're getting color removal as well too. So what I've seen is some municipalities that take on local landfill leachate. Sometimes if it's a significant enough part of the overall flow of their system and they have UV disinfection, it can cause problems. Or even we're working with a pharmaceutical group that had a really high level of color, and we'll see some of those pictures too. So getting that color destruction will help with UV transmittance as well too. So it's kind of a nice kind of benefit to what's happening, you know, while we're targeting these other contaminants. And so here you can see kind of the different species. As I kind of mentioned before, you know, getting that 40 to 60% COD removal, so not complete COD destruction, but getting complete ammonia removal. And then we happen to also look at phosphorus at this case too. And then you can kind of see some of the numbers. We also saw about 50% boron removal. The client actually tested this. All the other data though was done at the University of Massachusetts. And so there was some phosphorus destruction, but it's definitely something where if you had a really low phosphorus limit, you probably need to add a chemical or like a flocculation, coagulation, and then also a screen too. So that's kind of all of the data that we run actually through the pilot unit itself. Depending upon the concentration that we're looking at, typically we'll run anywhere from like 5 to 20 gallons per minute through that actual pilot. And then the rest here is some of the bench test work that we've done with UMass. So this first one here, you can also see the color destruction, and it's hog farm waste, which is nasty, high concentration COD, high concentration ammonia. And we were actually looking to be a pre-treatment step before the biological process. The major driver in this instance was because that ratio was off, where the, I'm sure you know, to get good biological removal, you want that perfect BOD to ammonia to phosphorus ratio to get good destruction, and the ammonia was really high in this case. So we sized the system to get the right amount of ammonia destruction to then send it to the biological process so that it can run optimally. And you'll kind of see here. So we went from 0 to 30 minutes, though in this instance, we didn't take the process that far since it was getting further treatment, but you could get complete ammonia destruction if you wanted to. And here's kind of what those curves looked like for that sense. So again, you can also see here when you're running at really high levels, like at that higher concentration, you're getting a higher rate of removal as well too. And then it kind of slows down as the concentration decreases. And so here's kind of the actual values if you're interested. And then the other one that I kind of mentioned before is the kind of color destruction project that we're working on. And it looks kind of almost black in this picture, but it was basically like a dark blue, purple kind of color, if you will, at first. And it was causing issues to, they're actually sending it to the city sewer, to the downstream community, and affecting their wastewater, which is kind of a common theme. I'm talking to, they actually make liquid smoke locally here in the Midwest, and similar deal where the water is discolored. That's even coming out of the wastewater plant too. So the kind of add benefit of this technology is that you'll get that color reduction as well too. And so you can see in the photo here all the way to the right, it's practically clear, but we even actually tested for color. And so I think I have some charts coming up. So here's, you can see the absorbance of the system. So that big curve is that really dark purple. And then as you go through treatment time, that curve reduces drastically. So we also happened to measure the COD destruction at this facility too, just to see what, if this was a pre-treatment step, then what would be sent to the city after this system. It's kind of a nice lineup of the photo. And then just to kind of give you a data summary of all of the kind of samples. So I think we have a little bit of time. So I'll go into some of the actual in-field pilot and testing data as well. So the nice bit of what we did with UMass was to really establish good baselines for ammonia removal. And then we did a little bit of testing with color and some other contaminants, you know, on a sample basis for industry, but some of this data is nice to show the destruction of different contaminants, if you will. So I'm going to jump ahead a little bit, sorry. This one out in Quebec, what was interesting that we saw not just an ammonia destruction removal, but we saw a reduction in sulfides as well too, which was cool. So, you know, helping with odor and that discharge issue was kind of an added benefit in the sense that we hadn't necessarily anticipated. I know sometimes landfills also worry about phenols and polyvinyls, and so we've gotten pretty good destruction of both of those at this landfill. And then also this particular landfill in Tennessee too. And so, you know, one thing that is unique about the process is it's not like you know, a lot of folks in these instances will do like an MBBR. So you have that biology that's getting the removal for you. If you're not always needing to get treatment, sometimes it's difficult when you don't have enough food, right, to feed your biological system. In this sense, whether it's, you know, a community that has fluctuating flow rates, or like with a landfill where it's so dependent upon rainfall, you can actually shut the system down and you don't have to worry about kind of keeping that biology alive. So it's a good option for folks that either don't run very regularly or need to be able to run intermittently as well too. And then the other thing as well as we kind of progress the technology and as we learn and pilot, we're able to kind of reduce the cost of the system as well too, as we kind of dial in treatment. And then also, we can very easily augment the process. So if you are running at a high concentration, like a pretreatment system, and you just want to get to 40 or 50, like a typical municipal level, we can really nail down the process to save energy to just get the removal that you're looking for. But of course, we can size the system to complete destruction or redundancy and things like that too. But I think that process control component's really critical in making sure that, especially this particular technology, doesn't take up too much energy to run.
Thank you very much. I do have one question for you. Have you worked with any side streams inside of municipal wastewater treatment plants where the concentrations are higher? Things like, say, dewatering applications? So not like a full piloted a...
like in a side stream ammonia treatment?
Yeah.
Yeah, exactly. we'd really like to. I've looked at the University of Massachusetts, you can take their supernatant stream and treat that. So currently we've run high concentrations, but we've not piloted a side stream ammonia treatment from municipal waste, just really high industrial waste. But I would love to try it. I also am curious too, since a lot of those streams have quite a bit of phosphorus in them as well. And so it'll just depend on what all you're trying to get removal from, but I think it could be a good alternative to some of the other ammonia side stream options that are out there with kind of the nitrate shunt. I'm talking about technologies where you're kind of creating a really sophisticated biomass, which is cool. I think this might be a simpler option if you maybe don't have the operator capacity to really hone in on some of those more difficult to keep alive biologies out there that kind of do ammonia side stream treatment that's becoming popular right now.
It can be very tricky keeping the biological stuff up. We have one other question here from Bruce Zuiers. How much power does this run for a typical municipal system of 20 cubic meters per day? Sorry, did you catch that?
I did, yep. So 20 cubic meters per day. Typically, I just did, we're working on a proposal up in upstate New York, and it was comparable to the amount of energy that they were consuming in blowers to operate an MVVR.
Okay.
If that helps, sorry, I don't know. I'm like trying to convert really quick. But I would say it's fairly close when you're talking about ammonia removal for a municipal system. So it's not, right now, it's not like a huge energy savings per se. I think the overall energy savings are in the fact that you're not creating biosolids. Otherwise, if you're looking just at the actual process, it's kind of a wash with a typical, in this case, MBBR. Potentially, if you're looking at an MBR, it might be a little bit less energy than that, but it'll depend on what type of membrane you're looking at there. So I can, if you don't mind, I can send you like an actual value once I pull up some of the numbers, but to give you a feel, that's kind of what I've seen.
I think you gave a range there. I think Bruce is happy with that. I've got another question here from a Lawrence Baseline. The HRT, does the water have to sit stagnant in the electrodes containers during the treatment process? Or is it a flow through?
We actually prefer to have it flow through. Often if we're running a batch, it's because we have a limited amount of sample, or to save energy, or sorry, not to save money on just the testing. But when it comes to all the actual piloting, it's better to flow through the system. when you're getting that more turbulent flow through the reactors and how it's kind of designed, you're going to get a better rate of removal. So the reaction actually happens better because those oxidative species that you're creating actually come in contact with more of the contaminants better. So we want things to be turbulent. I suppose it doesn't have to be, it will still work, but ideally we'd run as a flow through system with the right amount of turbulence through those reactors, yeah.
Okay, well, thank you very much.
Yeah, thanks so much.
It doesn't appear that we have any other questions. So I want to thank you from the EOCP and for attending the conference and presenting for us.